Hey guys, so today we are doing Unit 6 Exponential Functions. As for my part, I'm doing 6.2 Evaluating with Integer Exponents. So first things first, an exponent is a number that tells how many times the base number is used as a factor. For example, 3 to the power of 4 indicates that the base number is 3 and is used as a factor 4 times. To determine the value 3 to the power of 4, multiply 3 4 times, which will give you 81. Exponents with bases that have an odd exponent will give you a positive answer. For example, 4 over 10 to the power of 2, which equals to 16 over 100. And how I got that answer was that I brought the power down to both the numerator and the denominator. So I did 4 to the power of 2, which is 16, 10 to the power of 2, which is 100. If a negative number is raised to an even power, the result will be positive. For example, negative 2 to the power of 4, which equals to 16. And as you can see, I multiplied negative 2 4 times to get my answer. If a negative number is raised to an odd power, the result will be negative. For example, negative 2 over 5. Once again, I multiplied negative 2 5 times and got negative 32 as my final answer. Now, when doing a fraction as part of your final answer, putting a negative number in the denominator of a fraction will result in the answer being incorrect, as it's not acceptable to do so. You can either move it to the middle or at the top of the fraction. So here's an example. Negative 4 over 6 to the power of 3. So what I did was, obviously, I brought the negative to the numerator, which is 4, and then I brought the power down to both the numerator and the denominator. So I did negative 4 to the power of 3, which gave me negative 64, and then 6 to the power of 3, which gave me 216.
Hey guys, today we're going to be doing 6.3, investigate rational exponents. Okay, to convert n to the square root b bracket m into b to the power of m over n. First of all, you're going to make your m into the numerator and your n into the denominator, and you're going to keep your b the exact same. Alright, that's going to be your base. Alright, let's go to 1. Okay, so you're going to solve this in your calculator. You're going to put 100 to the power of 1 over 2, and that's going to be 10. And if you're just like b, you're also going to do the exact same. So you're going to put 1,000 to the power of 1 over 3, and that's going to equal 10. E. Alright, so you're going to put bracket negative 100 bracket to the power of 1 over 2 in your calculator, and you're going to get error. So that means this is not possible. Okay? And in F, right? See, there's no m. There's no m. So by default, your m is going to be 1, and then your equation is going to look like this. So 1 negative 1,000 to the power of 1 over 3. That's what it's going to look like. 2. So first of all, you're going to put 16 to the power of 3 over 4, and you're going to get 8. Okay, but in E, there's something different. So in E, there's a negative in the exponent. So you're going to write down 1, something different. There's a negative in your exponent. So you're going to, after you notice there's a negative, you're going to write out 1 over 16 to the power of 1 over 2. And from there, you're going to get 1 over 4. And that's it.
6.5 functions are shown through function notations, which is fx equals a to the power of x is greater than 1. Your graph should look something like this. It increases as it moves to the right, but is still positive. The graph will be the opposite. It should look something like this. It increases as it moves to the left. Since a is greater than 1, we already know that the graph will be increasing as it moves to the right, but to find the y values, we need to sub in x. Negative 2 would be 0.1. 3 to the power of negative 1 would be 0.3. Anything to the power of 0 is 1. and 3 to the power of 1 is 3. 3 to the power of 2 is 9. This is what it should look like. The domain would just remain as XER since it's never ending on the x-axis. The range would be YER, y is greater than 0, since the graph does not go below 0 on the y-axis. The line crosses through the y-axis at 1, so that would be our y-intercept, 0 and 1. And the asymptote is always the x-axis.
My name is Tanya, and I'm going to talk about how you can use a table of values to find if a relation is a quadratic, linear, or exponential. So I know that this table is a linear. It will be a linear relation because the first differences were the same. I didn't need to find any second difference or ratio to figure it out. I know that 4 minus 6 is negative 2, 2 minus 4 is negative 2, 0 minus 2 is negative 2, negative 2 minus 0 is negative 2, negative 4 minus negative 2 is also negative 2, and negative 6 minus negative 4 is also negative 2. So those were my first differences and they were the same. I know it is a linear. Moving on, this is a quadratic relation. I did 0 minus 6, which is negative 6, negative 4 minus 0, which is negative 4, negative 6 minus negative 4, which is negative 2, negative 6 minus negative 6, which is 0, negative 4 minus negative 6, which is 2, and 0 minus negative 4 is also 4. Now, because that the first differences were not the same, I know it's not a linear. I had to find my second differences, which I did was negative 4. I minus these two numbers, negative 4 minus negative 6, which equals to 2. Negative 2 minus negative 4, which is 2. 0 minus negative 2, which is 2. 2 minus 0, which is 2. And 4 minus 2, which is also 2. Because my second differences were the same, I know that this would be a quadratic relation.
This course covers exponential growth and decay. Exponential functions can be used to display growth and decay in graphs. This is used in everyday life constantly. For easily portraying things like population changes, bacteria growth, radioactive element decay, and naturally occurring phenomena, I have created 4 examples of exponential growth and decay in the form of word problem scenarios. We will go through each of these scenarios and solve them for an answer. The first example I've created is of population. Usually, the population of a city is constantly growing, exponentially. For my example, we will use the ancient city of Rome. In 100 BC, the population had reached about 4 million. If the population kept increasing at a rate of 12% every 10 years, what is the population at 0 BCE, 100 years later? So for this, first we have to find out the PF, the PI, the rate, and the period, which is the R equals rate, H equals period, and PF stands for final population, and the PI stands for initial population. So for this scenario, the initial population is 4 million, the rate is 12% or 0.12, and the time involved is 100 years, and the period is 10. So our formula would be 4 million brackets 1 plus 0.12 to the power of 100 over 10. After using this formula, we would find out that the population of Rome at 0 BCE would have been 12,423,392. Scenario 2. The next scenario I'll solve is about bacteria growth. Most of us learn in biology that bacteria grows by doubling itself. In the same way, some viruses do too. You work for the Centers for Disease Control. You've been called in to project the spread of the disease. On your report, it is predicted there are 124 virus cells currently. The virus doubles every 5 hours. How many cells are there after 4 days? So for this, the initial population, which would be the of the cells, would be 124. The rate is 2. The time is 4 days, which is 96 hours. And the period is 5 hours. So after using our initial formula, which is final population, which equals initial population brackets times r to the power of time over period. So after solving, there would be 74,678,846 cells at the end. Scenario 3. Now that we've explored exponential growth, we will look into another important aspect of this section, exponential decay. This is used by chemists when calculating the half-life of radioactive elements. So, for this scenario, you are a government chemist. An alien element has crash landed onto Earth. The element is radioactive, therefore no scientist can go near the element and do tests on it. But your colleagues have figured out that the initial weight, which is 30 kilograms. They also determined that the element has a half-life of 50 days. The scientists can only approach the element when the weight is below 5 kilograms. After how many days can the scientists approach the rock? So for this, the final amount, which is AF, the initial amount, which is represented by AI, and the period, which is represented by H, and time, which is represented by T. So our formula would be AF equals AI bracket 1 over 2 bracket to the power of negative time over period. So for this one, our final amount would be 5 kilograms, our initial amount would be 30 kilograms, and our period would be 50. So after solving, we'd figured out that the scientists can approach the alien element after 28 days. Scenario 4. The last scenario I've created is one where suppose you are an environmental scientist. You have been studying an iceberg for 15 years as of today. When you first started studying, the iceberg weighed 10 million tons, but because of global warming, your iceberg is melting 2% every year. What is the weight of the iceberg today? So after solving using the same method as scenario 3, we would figure out that the iceberg has melted by 2% every year for 15 years. So that would mean our weight is 2% or 0.02. The time is 15 years and the period is 1. So after solving using the formula, we figured out that the iceberg will weigh 73,856,091 tons today.